Alright, so in this last video of our Madden-Julian Oscillation video series, we're going to talk about ways that we can monitor the Madden-Julian Oscillation utilizing real-time data, such as that representing thunderstorms in the form of outgoing long-wave radiation, as well as atmospheric analyses of zonal wind, particularly in the lower and upper troposphere. We'll also use this information to talk about the phases of the Madden-Julian Oscillation that we've previously introduced in earlier videos. So let's get started. So when we introduced equatorial waves and discussed how we can monitor those, we talked about how they each had distinct signals, distinct power or amplitude at certain frequencies describing their return period, as well as certain wave numbers describing their horizontal scale, as well as their direction of propagation. We would then identified that we could see Kelvin waves on the symmetric side here, moving to the east at relatively large wave numbers, but with a wide range of allowable wave numbers, between about 3 and 10 or more days. We also had equatorial Rossby waves that moved to the west at relatively small wave numbers and very long periods, and mixed Rossby gravity waves that moved also to the west with an antisymmetric structure across the equator and relatively short periods compared to the equatorial Rossby waves. We can use this same filtering approach to take, for instance, outgoing long-wave radiation data and filter it based off of certain wave numbers, certain frequencies, and certain structure across the equator. And here we get the Madden-Julian oscillation with this strong signal that we see, particularly below wave number 4, so wave numbers 1, 2, 3, and 4 here, at periods of 30 to 60 or more days. Primarily within the symmetric range, note the bright pink coloring that we see here, indicating that there's a lot of signal at those wave numbers and frequencies. But there's also a little bit here on the antisymmetric side associated with the seasonal variability in the latitude at which the Madden-Julian oscillation is found. So with this information, we can isolate within any sort of data utilizing Fourier analysis the frequencies and the wave numbers of interest, and then back transform those into physical space to be able to identify and track the Madden-Julian oscillation. And so doing so, we get charts like the one that we have here at left, where the color shading is outgoing long-wave radiation anomalies, where the blues and purples indicate reduced outgoing long-wave radiation and thus enhanced thunderstorm activity, and the yellows, oranges, and browns indicating elevated outgoing long-wave radiation and thus suppressed thunderstorm activity. So we can do this filtering because those small wave numbers and long periods moving eastward are unique to the Madden-Julian oscillation. And here we get a series over a 2-year period of successive Madden-Julian oscillation active and inactive events. These are primarily contained within the Eastern Hemisphere, consistent with our earlier discussion of this being where the Madden-Julian oscillation has its greatest amplitude. This dashed line here in the middle is the international date line. There's very little contouring to the east from there. We can see signals that traverse eastward over relatively long periods of time, the solid lines indicating the active phase of the Madden-Julian oscillation and the dashed lines indicating the inactive phase. But note how it's highly irregular. We see several successive events here and then some more gaps as you get later on into that year. It's highly irregular in terms of how far east any individual event travels, also in terms of how far west any individual event actually forms, and thus how long a particular event lasts. So we see those active MJO events that are often followed by inactive events, but they are somewhat irregular in this structure. I'll also note that these total outgoing long-wave radiation anomalies, given by the first color bar here, are generally about 10 to 50 watts per meter squared on either side of 0. Whereas these contours here listed up at the top, the contour interval is 10 watts per meter squared. And we generally only have 1 or 2, at rare times 3, concentric contours. So the Madden-Julian oscillation's outgoing long-wave radiation anomalies are somewhat weaker, about 10 to 20 watts per meter squared. So on average, we're looking about 25 to 50, sometimes even a little bit more, of the total outgoing long-wave radiation anomaly is associated with the Madden-Julian oscillation's active or inactive phase. There's another way that we can use to be able to identify and monitor and track the Madden-Julian oscillation, and that's through what is known as empirical orthogonal function analysis. So this is a statistical tool that allows you to identify modes of variation within time series data. So for instance, maybe we have outgoing long-wave radiation data around the globe at the equator. So we have horizontally varying data at one time. Then we have many successive analyses of that outgoing long-wave radiation data, perhaps every day, over a year or 10 years or 30 years, as the case may be. So that's what comprises our time series data. And it need not just be one variable. And in fact, as we'll show for the Madden-Julian oscillation, we also include zonal wind in the lower and upper troposphere alongside that outgoing long-wave radiation. So usually we do a little bit of frequency filtering. We don't explicitly need to do this, but it helps to be able to hone in on the signals associated with the Madden-Julian oscillations 30 to 60, 30 to 90 day period. So we can remove higher frequencies and lower frequencies from the data so that there's less of an effect of equatorial waves, as well as El Nino Southern Oscillation and other longer period variability that feeds into the total outgoing long-wave radiation data. It's imperfect. Even those longer period features like ENSO still have structures on these shorter timescales that can show up in one of these analyses. But doing this frequency filtering helps to mitigate their effect on the overall analysis. So we typically do this prior to the EOF analysis just to retain the Madden-Julian oscillations frequencies and about 60% of the variability on these time periods. Here specifically 20 to 100 days, but really 30 to 90, 30 to 60, anywhere in that range. Most of the variability in that time period is uniquely associated with the Madden-Julian oscillation. We can use outgoing long-wave radiation data alone, we could use zonal wind data alone, or we can combine the two to be able to get at the Madden-Julian oscillation structure. The seminal, or the historically most important work in this area, is Wheeler and Hendon of 2004. And they used all three of those variables: outgoing long-wave radiation, 850 hectopascal zonal wind, and 200 hectopascal zonal wind in the equatorial region, averaged on either side of the equator over a short distance, to be able to identify the Madden-Julian oscillation. And when they put those data into an empirical orthogonal function, or EOF analysis, they found that the two leading modes of variability account for 25% of the data's total variability. So they do a good job of highlighting the core structures of the Madden-Julian oscillation without getting bogged down in smaller scale, shorter period variability that also are present within the data. So as we'll show in just a moment, these two leading modes of variability have distinct MJO-like structures. So here on this slide, we have what those two leading modes of variability actually look like. The first one is dubbed EOF1, and it's here at the top. The second one is dubbed EOF2, and it's here at the bottom. They explain about 13 and 12% of the total variation in the data, respectively, and thus the sum of the two is 25% of the total data. So if we focus on EOF1 here, this solid line is outgoing long-wave radiation anomalies. This long dashed line is 850 hectopascal zonal wind anomalies, and the short dashed line is 200 hectopascal zonal wind anomalies. And so this depiction here identifies the positive EOF1 structure. So for outgoing long-wave radiation, it is positive between 0 and about 75 east. It is negative between about 75 and 180 degrees east. It's near 0 to about 120 degrees east, and then positive from 120 degrees east back to 0 degrees, or 120 west to 0 degrees. So where it's positive, outgoing long-wave radiation is enhanced, and that's associated with reduced thunderstorm activity. Where it's negative, it's associated with reduced outgoing long-wave radiation and enhanced thunderstorm activity. In terms of the zonal wind, this long dashed line being the 850 hectopascal zonal wind, it's primarily westerly or positive in the eastern hemisphere and primarily easterly or negative in the western hemisphere. The 200 hectopascal zonal wind here in the short dash is largely the mirror opposite. It is easterly, negative in the eastern hemisphere, and westerly or positive in the western hemisphere. So right around this area of suppressed outgoing long-wave radiation and enhanced convection, enhanced thunderstorm activity, we have low-level winds that are converging and upper-level winds that are diverging. So this is structured here around 120 degrees east, which is around the maritime continent. So this EOF1 structure is associated with the MJO's active phase centered over the maritime continent. EOF2 has a similar structure but shifted somewhat to the east. We have this broad area of not quite as large negative outgoing long-wave radiation anomalies between about 120 east and about 120 degrees west, with low-level westerlies here to the west and weak low-level easterlies to the east, and then upper-level easterlies to the west and upper-level westerlies to the east. So again, we have low-level convergence into this region in the central equatorial Pacific Ocean with enhanced thunderstorm activity and upper-level divergence within that region up top that feature. So these two EOFs, EOF1 and EOF2, are well correlated to each other, but with about a 9-day lag, representing the approximate time on average for this convectively active region near the maritime continent to propagate eastward into the equatorial Pacific Ocean here, such that, a cycle through all of these EOF structures, looking like EOF1 here, looking like EOF2 here, and looking like the inverse of each of these as the MJO event propagates around the globe, takes about 35 to 40 days, consistent with the MJO's overall period. So these allow us to be able to define phases of the MJO. We've previously introduced the idea that there are 8 phases of the Madden-Julian Oscillation. These are based off of the values of EOF1 and EOF2 when applied to real-time data. And so we have here cartoon schematics of the MJO circulation in the zonal plane, so the zonal overturning circulation associated with the active phase of the MJO with this convectively enhanced area here, and the suppressed phase with this downward motion through here, and then again through here as well. And so phases 1 and 2, the top ones here labeled F and G, or 1 and 2, are associated with data that look like the inverse of EOF1 from the previous slide and the inverse of EOF2 from the previous slide. So that would mean suppressed convection in the maritime continent and extending out into the Pacific Ocean. And in fact, that's what we see here. Our convective maximum is actually located back in the western Indian Ocean between about 60 and 100 degrees east longitude, whereas we have suppressed convection out ahead of that. So this matches with what we would expect from the previous slide's analysis. Phases 3 and 4 are like the positive sense of EOF1, so just like we saw on the previous slide, but negative EOF2, so the opposite of what we saw on the previous slide. So this would imply convection enhanced in the maritime continent region, but not so much as you get out into the Pacific Ocean. And in fact, that's what we see with these two positive convective anomalies here between about 100 and 140 degrees east longitude, roughly the longitudes of the maritime continent. Phases 5 and 6 look like positive EOF1, so just like we saw on the previous slide, and positive EOF2, so again, just like what we saw on the previous slide. So this would imply enhanced convective activity stretching from the maritime continent out into the western and central equatorial Pacific Ocean. And that's what we see here with these two enhanced thunderstorm regions propagating toward the international dateline, here 180 degrees longitude, and even slightly east of there into the western hemisphere. Although noting that the amplitude of the MJO typically decreases as you move into this region, climatologically speaking. Finally, phases 7 and 8, as we have here at bottom, are like the inverse of EOF1 from the previous slide, so implying suppressed convection in the maritime continent area, but positive EOF2, so implying enhanced convection into the equatorial Pacific Ocean. And we see the suppressed phase of the Madden-Julian Oscillation with tropospheric deep descent here between the eastern Indian Ocean through Indonesia and the maritime continent. And so just reiterating this for phases 5 and 6, positive EOF1, MJO active phase near the maritime continent, positive EOF2, active phase in the equatorial western Pacific Ocean, And so these two phases represent the active portion of the Madden-Julian Oscillation propagating from the maritime continent to the Pacific Ocean. We can use this information to create what are known as phase space diagrams, like the one that we see here at left. So we can take real-time outgoing long-wave radiation data and zonal wind data from, say, a model analysis and see how well they match EOF1 and EOF2. And the metrics of how well they match are known as RMM1 and RMM2. So positive values of RMM1 and RMM2 indicate direct matches to what we saw for EOF1 and 2 a couple of slides ago. So a positive RMM1 would imply real-time data that looks like the MJO's active phase being near the maritime continent. Positive values of RMM2 would imply the MJO's active phase somewhere between the maritime continent and the central equatorial Pacific Ocean. Conversely, negative values of RMM1 and RMM2 indicate inverse matches. So a negative RMM1 would imply suppressed convection near the maritime continent, and negative RMM2 would imply suppressed convection into the equatorial western and central Pacific Oceans, with the corresponding zonal wind fields matching each of these, whether it's positive or negative. The magnitudes of RMM1 and RMM2 indicate the matches quality and or larger anomalies. So if you have a large value of RMM1, that's not just a better match to EOF1, but it's implying that the zonal wind and outgoing long-wave radiation anomalies associated with the real-time data are particularly large. And likewise for RMM2, it would imply a better match to RMM2 to EOF2 structure, and that the anomalies associated with the real-time data are particularly large in magnitude. So tracing these through time provides the phase space plot here at left. So this is from November 21st, 2021 through February 18th, 2022. And it starts here where it's labeled start with the dark green line here in the middle of the circle. So this indicates a small value of RMM1, which is along the x-axis, and a small value of RMM2, which is along the y-axis. From here, this becomes slightly larger, particularly for RMM2 on the negative side, indicating that the MJO is in phase 3 with its convectively enhanced phase in the Indian Ocean. It then begins to move in a counterclockwise fashion around this plot here, where RMM2 becomes closer to 0 and ultimately positive, while RMM1 remains below 1 on the positive side. So this is associated with the Madden-Julian Oscillation's active phase propagating from the eastern Indian Ocean across the maritime continent into the western Pacific, and then ultimately into the eastern Pacific in the western hemisphere, as it moves from phase 3 to 4 to 5 to 6 to 7 and to 8. So this is associated with changing values, first of RMM2 as it goes from negative to positive, and then of RMM1 as it goes from positive to negative. As we move through time into January, which is the lighter green portion of this line here, both RMM2 and RMM1 become closer to 0. And so whenever the trace ends up within this circle line here, within a radius of 1 from the center, we say that the Madden-Julian Oscillation is too weak to identify. So we can interpret this here as the decay of that particular event of the Madden-Julian Oscillation as it then comes back here into the center. But then finally, as we move into February with the blue line here, note how RMM2 becomes increasingly negative, and we see the MJO's active phase emerge once again here in the Indian Ocean, and we start to see the trace propagate to larger values of RMM1 over time. So the Bureau of Meteorology in Australia and a number of other sources provide real-time as well as historic information about this, allowing us to trace just where the active phase of an MJO event is located. It's not a perfect analysis. Keep in mind that the data going into this, about 60% of the variability is associated with the Madden-Julian Oscillation, leaving 40% with other features. Furthermore, the EOFs only represent 25% of the variability in the data, and so there is variability that's not being captured within this analysis. But by and large, this does a really good job of being able to help us monitor in real time and in a concise fashion that does not require us to squint at loops of satellite imagery, how the Madden-Julian oscillation is evolving. So finally, we can use this information to go back in time and identify days in which the Madden-Julian oscillation was in any of those 8 phases for its active contribution. And so that allows us to create climatologies or composites of fields such as outgoing long-wave radiation and 850 hectopascal wind. In this case, it's the total wind, although you could consider just the zonal wind as well. So here we have the MJO's active phase associated with this dark shading indicating suppressed outgoing long-wave radiation, originating in the western Indian Ocean and then propagating eastward through the maritime continent into the Pacific Ocean as we go from phase 1 through to phase 8, with less of a signal in the western hemisphere, although you can kind of see an enhanced area propagate through here in that image. We can also see the MJO's inactive phase with these brown arrows and the hatching as opposed to the color fill, extending ahead of the active phase through the maritime continent into the Western Hemisphere, as well as trailing the active phase from Africa through the Indian Ocean toward the maritime continent. The amplitude of these outgoing long-wave radiation anomalies should be no surprise that it is greater in the Eastern Hemisphere, with less amplitude, less extensive shading, and less dark of shading in the Western Hemisphere. The 850 hectopascal zonal wind anomalies, the vectors that we see here within each of the panels, follow from the outgoing long-wave radiation anomalies. So highlighting phase 3 here in the third panel and phase 5 here in the fifth panel, the vectors are directed from east to west to the east of the active phase and west to east to the west of the active phase, implying anomalous low-level convergence that would then facilitate rising motion through the tropospheric column, leading to suppressed outgoing long-wave radiation associated with enhanced thunderstorm activity. So these data are consistent with our EOF analysis and with our real-time phase space plots, just indicating the climatological structures of the Madden-Julian oscillation. We've seen other charts like this, especially in our most recent our previous video about the impacts of the Madden-Julian oscillation, how they propagate from west to east over the course of a number of phases and a long period of 30 to 60, 30 to 90 days. So we can use tools like this to help us identify where the Madden-Julian oscillation's active phase is in both real-time as well as historical data. So this wraps up our discussion of the Madden-Julian oscillation. Next week, we'll move into monsoons, which are impacted by the Madden-Julian oscillation, but also have much larger scale structure than just that associated with the Madden-Julian oscillation.